Okay, so I plan to do it earlier, but as usual, it ended up in submitting my grading of your review test at the very last day, so today was the deadline. What I would like to uh, present here, just for the record, is that everything should be available. In particular, there should be the solution of the corresponding task, which I check against your solution, so it should be okay. What I actually realized after printing everything out and actually letting you go through the exam is that it would be nice to have some grading tables so that you know how the individual points are distributed. Previously, I just indicated it by hand in text, so this is just different option. So here in theory, you should have the instructions how I'm planning to allocate the points for individual parts. And then you have one way of solving that. So this is basically up to you how you would like to do it. Then there are these influence lines, and eventually this structural example, when I copied as much as possible from the MATLAB script, which is available in PDF and also in the direct file. It seems that at least some of you did it exactly in the same way as I did. And there is something wrong with this link. I do not know what caused that. But you can also have a look at that problem in NVIDIA and try to check whether I did anything correct or not. So that's pretty much it. The number of points you will get for your solution hence should be deducible from these rules or from the solution. And so you are very much welcome to check that. If you think that something is unfair, just let me know. I will have a look where the misunderstanding arose actually. And the main motivation, at least for me, is that if you have a look at this grading table, I'm almost certainly sure that there was something in the assignment and also in this grading table which is not entirely clear. So if there is something which needs to be clarified, let me know, because then the future generation may benefit from it. This would be something which is a bit more tuned. So any questions, comments regarding that? If you are not happy about your result, or you scored more than also less than 50%, or you didn't have the opportunity to attend it, then you can reset it. Regarding the timing, my personal preference would be on the first final exam. But if this is inconvenient for you, this is too late, for instance, then you can also try to find out some other options. But I'm not entirely optimistic about my schedule in December. But I will do my best. Okay, so that's it from my side. Again, everything should be uploaded in Moodle. If in Moodle, actually, you will see your submitted file with no red edit text, that means they uploaded updated version, so please let me know when I will update it there. And again, please check whether all points which are deducted from which are deducted because of your solution, if any. So if these points were reduced in a fair way. So that's it from my side. Any suggestion, criticism, some inconsistency from your side, something which was not very clear in the assignment, for instance? All fine.
I've just received it. Maybe I will go through you later.
Okay. All right. So if there are no other questions except for the discussion after the lecture, then I can return to the major topic, which is again, this excursion to displacement method. But now we are really starting to move to the part which makes the difference. So what I was trying to explain to you last week, with some additional technicalities I will refer to if the time permits. I was trying to get you a bit acquainted or do some recap of how elasticity in more than one dimension works. I will not go to the full 3D story, I will say in 2D. If you recall what we did previously, this was this truss element, and then we added on top of that bending effects. So this is exactly what I had in mind. So now I would like to discuss or think about what this membrane effect in 2D elasticity means. If you go to the 3D, then this is something which is a bit more difficult to digest, and it's not entirely clear to do. So I started with some justification why this can be relevant in civil engineering, and there are two major points of application. One is load-bearing walls, and the second one is routine label corresponds to certain distributes, meaning that if you imagine them as a three-dimensional bodies, then you have two dimensions of the structure which are roughly comparable, and then you have this third direction, which is either very small or very large, so it's extreme in some cases. If the out-of-plane dimension is small, this arising problem is usually referred to as plane stress, as shown here, which actually means that there is no stress in the perpendicular direction, and the structure can freely expand or shrink in just perpendicularly to the center line. Whereas the other case, in which the thickness is very, very large, this is very massive structure, it actually turns out that this cross-section, which you can imagine anywhere within the structure, cannot deform out of its plane because there is this restraining part of the structure preventing that, and hence there is no displacement, and as a consequence there is also no strain in the direction perpendicular to the XY plane, and hence the name plane strain. So these are the two major applications, and again, using this plus some knowledge about plates, which I will develop in the very last part of the course, this is something which should be sufficient to get you acquainted with modeling most of the civil engineering structures. So then I started with a little recap. So the approach I try to take is that I borrow what I used from the previous course on the strength of materials or applied elasticity, and just try to discuss how things work in 3D. I'm very much aware that depending on the previous education, you might not see that, or the chances that you remember every fine detail that are also extensive, I would say. So I'm really trying to process it slow such that we are not getting lost. And what I'm trying to show in particular that this multidimensional elasticity is just one-dimensional elasticity plus some specialties which are really typical of mechanical problems. So what I try to explain first is that if we are in 2D, well, as the name suggests, by definition, there is no explicit dependence on the z-coordinate. So this is what we take into account with some degree of approximation, which I will briefly comment on afterward. This W, this out-of-plane displacement is 0. So this is something which is valid for plane strain. For plane stress, this is somehow, this is a bit inconsistent, but we can somehow argue that this contribution doesn't matter in this particular case, which boils down of having two independent displacement components. On top of how things are usually taught in this elasticity, I wanted to make the argument that in general case, continuum mechanics of solids distinguishes two configurations of your body. One is reference and the other one is deformed. Then these displacements, as they are shown here, they correspond to something very graphical, meaning that if you pick an arbitrary point or particle in the reference configuration, traces movement to the deformed one and connected by a vector, then the displacements u and v's are components of the vector. But in civil engineering applications, these displacements are usually very, very small, and although this is a bit more physical, it actually pays off at the end of the day to say that because these u's and v's are much more than characteristic dimension of my body, I will just read one configuration, the original one, and I will not distinguish. Which has some consequences in terms of non-intuitive argumentation in certain cases, but on the other hand, it leads to linear problems which can be solved in stable manner. And what I also introduced is this displacement vector or displacement matrix or column, if you wish, which connects these two displacements and orders them as indicated on the scheme. Now I proceeded to the second and final part because I also discussed previously this numerical integration technique that we're using to the end of the semester. And I wanted to make you aware of the fact that if you go from 1D to 2D, we do not have just two strains, as one would expect, or as this usually happens in more conventional theories. But we also have this mode of deformation, which is called shear strain, and it will be associated with certain shear stresses. These two are relatively easy, so this epsilon x is exactly what we know from 1D. So if I was using that all the time, but I didn't need to distinguish whether this is x and y normal stress and this is dependent. If we repeat the same set of arguments in verbatim in the perpendicular direction, this will give us this strain in the y direction. And if you would like to account for the change of the shape, then as this picture suggests, it consists of two contributions. One is obtained by this partial derivative, and the second one is obtained by partial derivative. We assume that these derivatives remain small, and this is usually assumed in this particular way. And what I then try to explain is that if I have a look at these non-zero strain components in here, I can represent them in a similar way than in 1D elasticity, which said that the strains are derivative of displacements. But because we are in this more involved settings, there is not one displacement component, there are two, hence this underlining. There are three strain components, hence this underlining. And if you would like to rewrite this equation, we have this 3×2 matrix, which contains partial derivatives and it's usually called symmetrized radial or straight operator or symmetrized radial operators. And the reason why I did that was that with introducing this bit of extra notation, now I can write down my strain displacement relations in a way which closely resembles the one we say, but covers the general story. So now I would like to proceed in this line of argument. So having tackled strains, I will now proceed to stresses. So again, I do not know whether you remember all the details, but actually this is a quite complicated story, which corresponds to the fact that you imagine that you take some elementary volume out of your structure. On each of these surfaces, as they arise here, you have some internal forces which go with the name of stresses. In fact, there is similar relativity deformation one normal and two shear stresses which are acting in plane. And I can actually associate those with every force of these surfaces. So general three-dimensional stress state can be quite involved in particular. And what I would now, and what is done next, and this is the contribution, one of my contribution of Cauchy, this usually as the first one develop this kind of equation, is that you can now write the equilibrium equation in the x coordinates, y coordinates, and z coordinates, where x, y, and z are the coordinate axes from this picture in here. So this is not z, this is y. And you will write down the equilibrium equations for the finite segment, volume, and then the limit passage in the free orthogonal direction. This is eventually what you get. So the equilibrium equations in 3D are free because I'm able to write down these equilibrium equations with respect to three coordinate axes. They have the form of the partial differential equations. Equations means that here I have equality. Partial means that they obtain or contain partial derivatives. And the structure which follows from the geometrical construction is that if you imagine diagonal-like terms, they contain here this normal stresses. And then you have just the remaining components of the shear. So this is basically what you get as an outcome. So I like the argument in general, but it is not in my power to reproduce it. It's straightforward. So just assume for the moment that this is something you recall from the speed elasticity. So the hard work was done. And what we are now trying to argue is how these equations simplify if we go for this 2D elasticity case. So 2D means that nothing depends on z, so I can just imagine that I cancel out this contribution, this contribution, this contribution, and that contribution. Then because nothing is happening in the third direction, in the z direction in particular, I'm assuming that this equation is satisfied. And final simplification arises from the fact that because nothing is happening in terms of stresses and strains in the z direction, all partial derivatives with respect to z vanish. So I can also cross out that large one column. So now I get the final form of this elasticity equations in 2D. So they involve two normal stresses, sigma x and sigma y, and they contain on top of that one additional shear stress, tau xy. Then obtain, and then I have something on the right hand side which I will comment later because I forgot to comment it in the original case. Okay. So again, these are nothing else than elementary equilibrium equations in the horizontal and vertical direction, like in the first lecture of structural mechanics. But now I apply them to the concept of continuum and to the gymnastics. By the way, Cauchy is also known for being as one of the inventor of differential calculus, and this was one of the so I believe this motivation understand how elastic would be. Okay, so that's the standard presentation, but now I will slightly slow down just to make sure that then that we are on the same page. So I would like to repeat again that the sigma x, sigma y, and tau xy are only non-zero stress components which I take into account. So I have already prepared some scheme in here in which I have for every segment which represents this plane, actually, but in 2D slice, I have two segments ready, one which is perpendicular to that surface or to that line, and the one which is aligned. So which stress components are associated with the highlighted segments? So I have either sigma or tau. So what is your guess? Well, this bit which has been highlighted a moment ago, to which components will the stress these correspond? So these are so-called normal stresses. And they are called normal because they are acting normal to that plane with which the stresses are associated with. So these would be the normal stresses. So the ones which correspond to normal or actual force into perpendicular direction. So these are denoted by sigma in general, and this is how they look. Because these are elementary forces, I need to introduce some basic notation or basic assumption how they will be oriented if the stress is positive. So if I, for instance, have a look or zoom in for this segment here, what would be the index which I will introduce here in the subscript? What is your guess? X, Y, X and not Y. Yeah, exactly. Or if you wish, so these two are oriented in the same manner. Would the positive stress be oriented in this direction or in the opposite one? What is your guess? So would that arrow, if positive, move to the window or to the door direction? Yeah, exactly. So this direction as indicated. Why? Yeah, exactly. So if I just have at this outer normal, the one which I have just mentioned, it will just move, it will position in the same way as this arrow. So it will just point out of the body. And because the arrow which has just disappeared is oriented along with the coordinate x, I will just inherit this with the stress. So likewise, if I move on the opposite side in here, this would be again sigma x, but actually now the normal stress would be oriented in the opposite direction, because if I position myself in here, I will go to the free space, then I'm going just opposite to the x-axis, and hence this is the orientation. So does this ring a bell? Have you seen this argument before? Yeah. For instance, if you just plot this diagram of positive internal forces, this is exactly what this corresponds, because this is something very normal force. Other option is related to the fact that if the stresses, the normal ones, are positive, then actually this elementary segment is stretched in this particular direction. So you can imagine these two arrows just stretching your elementary segment. Okay? So now, logically, this would be denoted as sigma y, because this is the stress which acts in the perpendicular direction and also acts at a different plane or segment, if you would like to this way. Because the outer normal in this particular case goes down, so would the positive normal stress, and same thing goes on the opposite side. Because if the y components of stress is positive, then the body would be just stretched. Okay. So I have already used the sigma x, sigma y. So the only symbol which is this tau xy shear stress. So actually this is something I will copy to all remaining four segments as they are presented here. Oh. And the final thing which I need to decide is whether if the shear will be positive, whether this is something which should point upwards or downwards. So if I just concentrate on this particular shear stress acting here, if the shear is positive, how it would point? Bottom or, sorry, up or bottom? What is your guess? So this is mechanics, so it is constructed to be really foolproof as possible. So if this arrow points exactly in the same direction as the x-axis, then actually the perpendicular component would just fall. And now I can repeat this, yeah, but with more consistency than I just presented. So if you just repeat this argument over and over, you will find out that if there is positive shear stress, then actually this is how things are. And this nicely aligns with that concept of strains, if I just projected before, because if you imagine how your elementary volume would deform under this particular stresses, you will see deformation here on top. So this leads to this mode of deformation. This vertical one would leads to or corresponds to the way how things are deformed in the phi direction. And if you just imagine that you will apply these four forces simultaneously, this is exactly the shape to which this elementary rectangle would deform. So they are corresponding to each other because they are vertical. So I will come to that after. So I will just here make the note that the way how things are defined, if you do it consistently as we do here, there is actually natural consistency between stresses and strains, all components. And if you do this multiplication, you will get some volumetric density of the work and incoming forces. I'll come to that after I finish this. So the final thing which remains is to represent again even this reduced set of equations in this matrix format. So I will start with something which is given and I have not commented yet before. So I will denote this whole column by this shorthand notation, which looks weird. I do agree on that. So this x underline actually means that this is column, not number. Overline means that this is given, and this x underline is for lazy people like myself who do not like to fully expand these two dependencies. I, however, earlier forgot to mention what this stands for. So these are volume forces, so-called, or body forces, if you wish. Their physical unit is Newton per cubic meter. And it tells you that if you know, these are volume or body forces because they are associated with the body of your structure, so they are present everywhere inside the structure. And if I would imagine that I have 1 cubic meter of my structure, where this x over bar and y over bar are constant, then actually this is exactly the resultant which I look at. So again, this is something which is taken with respect to fluid. The most classical example are actually are relative forces which point downward for this choice of coordinates in the direction of the minus y axis. So this is the way how to incorporate solid-plate structure. But they can also arise from different sources, but this is something far most common. So this is just clarification of the stuff which I forgot to mention before, but now I just need to do, again, this reorganization to have my life a bit easier. So if I wrote first 2 normal components and the shear components of my strain, I know that just to get nice correspondence, I need to do the same thing with stresses. So I need to put here the stress components in the x direction first, then the stress component in the y direction. And here I will have the shear stress to xy acting within the structure. Now I'm doing that just because I would eventually like to say that this is my sigma underlined in the x coordinates, where I forgot to emphasize that x stands for this point as shown here. Again, I'm distinguishing the original from the so again, this short notation allows me to represent the full stress state up into the any 3 independent numbers or functions or positions. And finally, I also need to rewrite these 2 equilibrium equations. So one is the equilibrium equation in the horizontal direction, which reads as partial derivative with respect to x of sigma x plus with respect to y, but of the shear component. So I have already done this exercise last lecture. So I just imagine that I'm performing this matrix multiplication. What is here gets multiplied with this one. So this is this partial with respect to x. So I will just copy it here. The formula does not depend on sigma y because this is the equilibrium equation in the x direction. And I also have the derivative with respect to y of the shear strain. So stress, sorry. So if you just think about that, this is actually the collected effect of these 2 contributions to the equilibrium equation in the horizontal direction. And by the same argument, one can find out that these 2 contribute to the equilibrium equation in the vertical direction. No, sorry. So this gets multiplied here. So this is partial with respect to x. There is no sigma x, so this can remain empty or 0 if you wish. And this gets multiplied by that. which corresponds exactly to this component. So this is partial with respect to y. So this is something which I have as a result. Now I can use new symbol for it, again, to make my life easier. But if I do so, I eventually find out that I'm no longer authorized to do that because I have introduced it before, the same matrix, only in this column format. So what I now did is that I took this information and instead of writing in rows, I wrote it in columns. So the first column would obtain this partial with respect to x naught and partial with respect to y, which is what I see here. And the same thing also happens with the second column here and the second row. So actually I do not need to invent new sign for that. I can use the one which I use for strings, but I just need to indicate that I swap rows for columns. So this is what this transpose stands for. So that's how the equilibrium equations are written. And again, this is this symmetrized gradient transpose applied to the stress column equals to this x over bar on the right hand side, so the intensity is on the forces. So that's it. It is not entirely straightforward like for heat conduction or similar effects, but there are no additional effects of this type. There are only the normal components, or the theory assumes that, which are much easier to construct. So this is the opposite, this is more controlled. But with this additional complication, these are elementary arguments. But now comes the part which is not really super easy, I would say. And this is something related to constitutive characterization of my material. Because I voluntarily said at the very beginning of the lecture that I will treat it elasticity, then I know what I need. I need to formulate Hooke's law. Actually, it is something which we like to call a generalized Hooke's law, meaning that this is not for one bar under tension and compression, but this is for the unit state. And here, unfortunately, I do not have the chance to repeat the whole story, but if you, at least those of you who attended the classes by Jan Corel and this very nice lecture notes, you will find out that this is eventually the format which you get as an outcome. So what you have on the left-hand side is the full strain column, and this is full stress column. So it contains this three normal and this three shear components. This one corresponds to stress components ordered following the same logic. Now, if I assume that my material is isotropic, meaning that it responds to the action in every direction in the same way, this is usually noted for steel and concrete. We know that for food structures, for instance, or food material, this is something which is certainly not realistic because it has different properties along the fibers and the people. But apart from that, this is the most used models to check the structures for the surface state. And it actually turns out, if you do it from more theoretical perspective, then you need two constants of material to describe arbitrary isotropic material, and basically it is your pick to select those which you like more or less. I forgot to put here a link to Wikipedia, but if you write in English Wikipedia elasticity, it has a huge table which tells you how to convert different material constants to the other ones, assuming that your material is isotropic. But in the engineering computations, these are two constants which are prevalent. So They are present, for instance, here. So this E is something we have seen before, and this is Young's modulus. But there is now some additional parameter in the font which I selected for the presentation. I'm unable to distinguish this single U from E. So this is E. Has someone seen that before? Can you comment what this stands for? How you imagine that? So what is the name associated with that in this issue? So this goes with the French name of Poisson, whereas, yeah, and if there is some French speaking person, then I do apologize for my pronunciation. Young was British, so this is easy. And what is the meaning of that? Can someone give me a pointer how I can imagine that?
The ratio of how you deform sideways.
Precisely. So yeah, and this is exactly. Thank you. This is precisely the information which is stored in this first. In this first row. Yeah, in this first column. So if you just imagine that you have some, this elementary piece of material, not some cross section which is assumed to be rigid, but really it is 3D, and you assume that it is under the uniaxial stress of stable stress, so it is subjected to sigma x. So this is non-zero, these remaining vanish. These are exactly the strains the material will see. So it will see this stretch in the x direction. So the stretch which is associated with the load, but it will also contract, and it will contract in 3D actually in two ways, which are perpendicular to the load. So this is the one, and this is the one. So this represents the experimentally observed fact. If you load this material by stress, let the remaining part to be free, but actually the materials, the structure segment shrinks in the perpendicular direction. Okay, and this is exactly what this Poisson ratio tells you. Normal materials shrink, hence this minus is present here for aesthetic reasons, not to define material property, which is negative. But there are also some materials with internal structure which can expand under compression. It is basically some substructure in there. And this is one of the applications of fractal mechanics in modern engineering materials. So this is it. This is the explanation what the Poisson ratio is. Now, if you imagine that instead of putting it in the x direction, you will do it in sigma, in the y direction and z direction, you will get this block of matrix in here. So this is something which corresponds to normal component. So logically then, this entries here, they correspond to shear-like behavior, and there is additional material or additional constant which defines that. This is denoted as G usually, and this is something which is called shear modulus. I do not know what proper name should be associated with this. Perhaps something on, I don't know. This is how the theory goes. So if you now do the algebra, actually these entries, they represent the relation which tells you that the sigma something something, the strain, the shear strain equals to the shear stress with the same indices but normalized by this G. So this is just conventional Young's modulus type of behavior of shear. So again, this is something which is associated with Robert Hooke, one of presumably unsung heroes of 17th century, who, as I read again in the articles and in other biblical texts, was assumed to be part of Newton, but actually it but he did a lot of impressive things, by the way. It's a bit surprising, actually, or inconsistent to associate it with this name, because his original statement was assuming that this mu, this Poisson ratio, does not exist, so it's equal to zero. It was not written in terms of stresses and strains, but displacement and forces. And actually, the mode in which this holds really in the almost original version is in shear, not in the small stress, not the stress state, obviously the dimensional stress state that he originally imagined, but he was the first one to put the proportion into it, so this is why this is associated. Okay. So this is really something which holds for arbitrary 3D body. Isotropy, it can be deduced from by some geometrical arguments even that there must be this relation between these three constants, shear modulus, Young's modulus, and the Poisson ratio. But this is one of relations from a Weizsäcker, because there is also something which is called bulk modulus, which corresponds to pressure, like loading. Then there is the metric modulus, which is also denoted Raman modulus somehow, which is something which my colleagues from the Department of Geotechnics tells you. So it is not one-dimensional stress state, but one-dimensional strain state. So you know, if you have something deforming in the structure, it is not deforming because of this restraining part so much. So and there are additional options we can consider. But what is important is that even if you propose a million of these material constants, only two of them will be independent, and the rest will be expressed by those. So this is the easiest illustration. Other story can be made more elaborate. Okay, so now, well, back to the business, because I will now assume that actually I'm in the state of plane stress, as you can see here. Which means that I know again what my stress state is. This is something which is given, so which is input, and this is something which I get as an output. Okay? So if this is stress state, which is called plane stress, this is just to say that actually there are only three non-zero stress components, sigma x, sigma y, and tau xy in here. The remaining ones, they do not contribute. So now let's have a look at what the general theory of elasticity in 3D tells us. So if you just imagine doing this matrix multiplication and you copy here the components which I have been talking before, this epsilon x, epsilon y, and this gamma xy I was using before. And this is what I have as an outcome. And now if you imagine that basically you delete from the matrix the things which are multiplied by 0. So this one, that one, which is something I have done already many times. So now I will just repeat it. Then these are the only entries which survive. And if I'm interested only in epsilon x and epsilon y, that I can actually blindly copy this part of the matrix. So this is 1 minus nu minus nu and 1. Then here are zeros if I would like to be explicit. Here I have this shear stress to strain conversion. So here is 1 over g. But because I have this factor of 1 over e present here, which I forgot to copy the handouts. I just need to rewrite it in this slightly different format. So by that, I have actually incorporated this row, and that row. As for the remaining shear components, if you just imagine that you do this matrix multiplication, whatever these three stress components are, they are also always equal to 0. So nothing changes if I cancel those out. So far so good, but actually if you check it very carefully, it turns out that there is one part which is remaining, which is this epsilon z, that out of plane strain for plane stress, which by the multiplication is nothing else that minus mu over E times sigma x plus sigma y. Okay? So this is the first slight inconsistency in the theory, because I have originally assumed that there is no out-of-plane strain. I just cancelled it out, if you recall. But actually now I deduce that there is some strain. This strain is because of Poisson effect. And as you may imagine, in this particle scheme, if you have some thin sheet of material, you somehow stretch it in the center line because of Poisson effect, it shrinks in the perpendicular direction, and this is exactly what the theory predicts. So it turns out that there is certain inconsistency in this formulation, but it is not so much important because eventually you will work with this virtual work statement at the end of the day. And although this strain is non-zero, it is doing work by zero stress. So it does not contribute, but it just shows that if you take this general, the most general equations in 3D and try to reduce them, there is always a price to pay. So there are some inconsistencies. It is not so severe as in the theory of bending of thin beams, which predict that there is no shear in the cross-section level over that must be, but there are some ways to circumvent that. So here this is not needed because it doesn't contribute in the terms of the virtual work. So now this is my reduced matrix, but actually this is not what I need to do my computations. I knew I need to formulate it in the opposite way, in the way which Robert Hooke did, saying that the stress is proportional to strain, not the vice versa. And for that I need to do a bit of more detailed calculation. And now I discovered it eventually. So this is what I have already from my computation. So I have this expression. In here, and this is something which multiplies the stress components I'm considering. So this is what I have. Just to make it a bit more compact, I know that I already can denote these two columns as stress and strain, and this inverse stiffness or compliance, if you wish, is in the literature usually denoted by C. It is 3 by 3 matrix in this particular case, and it's called material compliance matrix. So if I know that, if I know that this epsilon equals to this compliance times stress, then to get the other way around, the only thing I need to do is to pre-multiply everything by the inverse matrix to C, which is a matrix which it multiplies the original either from left or right, gives rise to identity matrix, so the matrix full of ones. So what I get as a result is that the sigma, these three stress components, can be obtained by the inverse compliance matrix multiplying string. So the only thing which I need to do is now to invert this matrix, which I wrote in a completely stupid way, so sorry for that. If you have a look at its structure, it also reflects the underlying physics. I can decompose it into these subblocks. The ones which are zero take into account the fact that normal stresses do not interact with shear strain, stresses and strain. And this is just the shear level. So now what I need to do is actually to invert this 2x2 block separately, and then make sure that this is compatible with this. And if you recall the formula how to compute this particular inverse, you need to compute the determinant of this matrix, which is 1 times 1 minus u square, and normalize it by this contribution. So there will be something divided by 1 minus nu square. This is to be inverted. So this will be something like E. So this is the factor which arises in front of the matrix. Again, this is inversion of that. This is needed to be able to invert this matrix. And now, if you recall, you will just sorry. Sorry. No, that's fine. Sorry. Yeah. Sorry. So now, if you imagine that you do this multiplication of these two matrices, so what you get is 1 minus nu minus nu1 sorry, multiply. Sorry. This is separated by 0, 1 plus nu, 1 plus nu. Now you do this multiplication, so this is 1 times 1 minus nu square. If you do this multiplication, you will get 1 times nu minus nu times 1. And if you repeat the rest of the argument, this is what you eventually get. Sorry. So So I do not know whether we call it exactly, but actually the full loss was you inherit the other loss and then you write the remaining terms for the two makers by changing the sign in order to achieve this cancellation. And what I would like to see here is the shear modulus, because the last non-zero component is this tau xy. Again, what I would like to see here is the shear modulus, which I would like to remind you is defined by this condition, which I presented in the previous slide. So just to have it expressed in the equivalent form, here I have this E, so I do not need to add anything. Here I would like to see 1 plus nu, but I do not have it. But I recall that this 1 plus nu can be expanded as follows. So what remains here is actually a factor of 1/2 of 1 minus nu, and that's it. And sorry for writing it so inconsistently, but later on I will present a neutral version. So again, I'm aware that this is not completely straightforward argument, but well, this is how it is. The shear makes everything more complicated in one-dimensional theories. You can just do write line meters and those. For isotropic materials, these material properties are there. And also, this is something easy. Shear makes the life a bit more important for people who which is us in this course. So this is what you get. So if you give me this two material constants, Young's modulus and Poisson ratio for 3D problems, so measured on some sample which is three-dimensional, if they would be used in plane stress, meaning in low-bearing structures like situations, this is how the stiffness changes of them, and I would like to remind you, or you will see on the next slide, sorry, that this is something which is different from the general stress state. And again, this is because there is no stress in the perpendicular direction. So this is something which is incorporated in the argument. But as usual, there is no free lunch, so there is this non-zero spin component which I claim to make sure that it is not present there. So this is slight inconsistency, but here it is not energetic or in the sense of virtual work. So yeah. Sorry. So apart from my speaking difficulties, this is the most straightforward argument that I can give you. This is the argument which at least those of you who might be able to concentrate for this we're able to concentrate a year ago in this course, theory of elasticity, in this most involved, I believe, lecture, which speaks about three-dimensional elasticity. The argument there was very similar to this one, meaning that you write first this equation in the inverse mode, meaning that you take the stresses as an input and get strains. This is natural because this is how these two material constants were introduced for one-dimensional stress state, one-dimensional strain state. But then you realize in the previous lecture that actually you needed the other way around, as we did here. But in that case, you need to do this inversion of 3x3 matrix, which actually then, so of this block, which then gives rise to something different. So, these entries are different from general three-dimensional situation. So this is how this works in 3D. The formula is very complicated, but this is because these material constants were introduced for one-dimensional stress state. But here I actually have it more in the form in which I can introduce the one-dimensional strain state, like in shear techniques. So if I'm in a situation where I know there is no strain component in the z direction, so for this massive structures, I can use this general 3D expression and just take this knowledge on board, so I know there is no strain. I know by my assumptions that there are no strains in question. So again, by my assumptions, if I'm in plane strain, these vanish, these are equal to 0, which means that I can again cancel out the corresponding columns, but this is no longer for this compliance matrix, this is for the inverted version, so I have different numbers appearing there. And now, if you just do the multiplication, you will find out that I can introduce here again the stress component sigma x, sigma y, and tau xy by taking this remaining part, and that remaining part on board. No, sorry, this is wrong. In here I have zeros because nothing was written there. Then what I'm missing here, I'm sorry, this is a typo. I should have put this constant so you can just put it in front of that, and then again you repeat a story that here you would like to see the shear modulus, because again normal and shear components are independent. So here I would like to see G, which is E scaled by 2 times 1 plus mu. So I have it here already present. So this is what I do not need. I need to get rid of this fact, Tor 1 minus 2 mu, and I also need to introduce this 1/2 here. So I will just take the 1/2 in front of that. So again, this is just a normalization constant if I'm implying the multiplication of this with respect to the opposite one, with respect to the factor in front of the equation, that I will get the shear modulus. So again, this is perhaps not the most straightforward thing in the world, but I have actually identified these 3 non-zero stress components I was working before when writing down the equations, because there is no connection between normal and the normal and shear components of strain, and these are assumed to be 0, then this one also vanishes consistently. And the final bit which appears in the story is, however, the strain, the stress in the perpendicular direction. So this one is obtained by as E over 1 plus mu times 1 times 1 over times 2 nu, and yeah. And if you imagine what is the multiplication you are doing here, so you multiply by Young's, by Poisson ratio, is epsilon x, by this epsilon y, so this is something I can factor out, and I will get this sigma x plus sigma y as a result. So there is some strain in the perpendicular direction. This is reaction to the fact that actually the remaining very large parts of the structure prohibit my structure from deforming out of the plane, which is something the structure would like to do, at least for the Poisson effect. And this is just the action from the theory, what the reactions are. They depend only on the plane, in plane normal strains. as shown here, which can be related to something which is called mean strain or mean stress in the opposite case. And if I know and I'm able to solve my two-dimensional problem, I can then reconstruct them in the post-processing step from this. What is important to keep in mind that, again, if I have this massive structure, I do not have only the in-plane stress component, but I also have out-of-plane. It is not shear, but normal, and if I am using some criteria based on the stress state to decide whether the structure will fail or not, whether to use this assumption, because these stresses are invention of Cauchy, Watson, and people like that. But it has been written from the different sources of the information, of failure structure. So they perhaps are fictitious, but they have very, very clear practical effects. So the only thing which I was unable to use actually over the years I've been teaching different versions of the elasticity is what is the inconsistency hidden in the plane strain, because this actually tells that sigma z is not zero, but depends on x and y's, which does not violate the equilibrium conditions, because in those three-dimensional ones, then actually this normal stress is differentiated with respect to z, but we are assuming that this is constant with the thickness. But there must be something which I'm doing. There must be some inconsistency. Actually, I'm able to pinpoint where this occurs. So this is even more natural reduction. And one of the major modeling achievements in the Czech Republic was the modeling for REAP-10, construction in the 50s, where the things were computed manually, and the engineers / mathematicians responsible for that were using this kind of theory. And even with only human calculators, they were able to make quite decent predictions. So it just shows that this is something which works. Okay, so just to summarize everything together, I was actually robbing you from almost 1 hour of your life, just to summarize that even in multidimensional elasticity, I have equivalent of Hooke's law, meaning that the stresses are proportional to strains. The problem is, though, that because there are more of them, stresses and strains, the relation is much more involved. It depends on 3 cases. I forgot to mention that this is 3 by 1, this is 3 by 1, hence this must be 3 by 3 matrix. But the structure of that is much more involved than Young's modulus only. So of course it contains the Young's modulus, but also contains this Poisson ratio or shear modulus or some equivalent property plus stress strain state. So in principle, again, it says that it is proportional, but the constants of proportionality are also assuming, are also depending on the fact that you assume a structure to be in the state of plane stress or plane strain. We'll get different distributions of stresses and strains because of that. And again, this is not because I would like to solve 2 different versions of the problems, but this is what is principally corresponds to this happening. So that is the outcome. And we have very explicit expressions how these matrices look like. And I was trying to show you that you can actually get them by repeating the argument of the elasticity, but in a bit of simplified version. And through the process, you actually obtain some the expression of the missing information. Okay, so now this is what I have promised. So this is a nice version of those previous developments, with an embarrassing typo. Sorry, but I really didn't see it on the screen of my computer. So now, I was boring you a lot with the structural equations of one-dimensional elasticity. I was repeating that over and over. I would like to, for the hopefully final time, mention that there was this cross-section displacement in each direction, which we differentiated with the strain. Then I multiply this by EA, where E is the Young's modulus, but A is cross-section area. This is also some introduction argument. You get normal forces, which we differentiated, change the sign, and get an intensity of the distribution. If you recall these structures, you will be doing the same thing for bending, but this is something much better explained. So now, if I just repeat the story, just to see how how things correspond to each other a bit better, I will assume that I have something of unit cross-section. So this would be then stress, and well, this remains the same. So if I just would like to highlight something short. So this is what I have in two-dimensional elasticity. I have my U, but this is now not a single displacement. There are two of them. They depend on the full two-dimensional position. I have my three strain components, but I have ordered them in that column. I have the corresponding three stress components represented in the same manner, and I do not have the distributed load along the length. I have a distributed load through the volume. Okay. So now if I do or write down the connections I have been using before, if you recall, this was this matrix of partial derivatives. So this symmetrized gradient, as some people call it. So some better derivative, which takes into account two spatial dimensions and the particle structure we found under consideration. From the equilibrium equation, this is what I got. So this is minus gradient transposed. And well, I spent a lot of time and a lot of considerations. So now I can write that going from strain to stresses, I can use this D. And if I would like to go in the opposite way, I would use the compliance matrix, which I have shown for when stress, when strain, it would actually correspond again to the inversion of that thing which I got. So it will be some nasty expression. I have already said what the C is, so the only thing which I need to explain is that this is material stiffness matrix. And this material is important in this particle concept or context rather than concept because I need to distinguish elements in this matrix from material stiffness. So material stiffness and material property is related to single material point, and it tells me how the strains are converted to stresses. Element stiffness matrix is a conversion between local displacements and local forces. So it works in kind of similar way, but it is expressed slightly. Okay, so two observations then. The first one is that to have the analogy complete, I should have plotted here also this multiplication by 1 over E, which is the inverse. So this is something I will actually denote here by saying that if I take C times D, or this is better, I will say that my C is the inverse, no, sorry, this is the argument which I have not thought over properly, but the way how I should have said it is that my stiffness is my inverse compliance, because this is the way how I derive it in 2D. So this is inverse here. And if you just have a look at these two expressions, up to some underlining and the change of the symbol in here, they are exactly the same, and this is just because I was too lazy to put this over bar. Just not too much documentation. So what this shows are two things. One is that actually, in terms of the underlying logic, the equations of elasticity for a three-dimensional body are nothing else than something like thrust-like behavior. In principle, from a mathematical perspective, this is correct. In terms of engineering or in terms of applications, however, this is a bit of overstatement, because now all objects are more complicated, some more than others, because these are characterized by three numbers, these only by two, and this derivatives needs to be interpreted differently. So, now this is the structured matrix. This is its transpose version, which is also something which works in 1D, but because you have only one derivative, there is no way to see it. And this was the reason why I did this artificial transposition at a certain stage of my arguments. But again, from the underlying principle, these are exactly the same, except for the fact that, of course, if you expand everything, now these are very difficult ones to solve. But again, in terms of structure, they are exactly the same. And just to see the structure, the only thing how I can walk through the diagram following the arrows is to start with this. And sorry, I just wanted to say that, of course, this can depend on X in general. But in the applications, we will consider it. So what I will do first is that I will imagine my unknown, my primary unknown, which is in here, which is displacement, which I then applied with the symmetrized operator to get the strain. So to get here, then oh my, sorry, I was unable to already foresee these properly. So to go from strain to stress, I need to multiply it by the material stiffness. So this is what I will do also in the generic expression. I need to take the result and subject it to this minus transpose operation. And what I have on the right-hand side is this x over bar under bar as a function of x, intensity of distributed loads. I cannot resist just to mention that in terms of some explanation we were exposed in physics in particular, but also in mathematics 3. These are some differential operators. This is a gradient-like operator, and this is something which is called divergence. It applies to simpler objects and elasticity. They have quite intuitive, relatively intuitive explanations in terms of continuum mechanics or elasticity. This is the easiest explanation to find out. If there is something easier, please let me. So that's pretty much it. So again, I know this is slightly disorganized, so this is the nice version of how the so-called Lame's equations look like. So one-dimensional version is the one which we have already encountered. If I just say that the cross-section area is 0, this is its multi-dimensional expression. Again, the main motivation for this is to show that actually there is one-to-one correspondence between different objects. So everything is the same, except for the fact that if you go to 3D, something surface, like, that is there, is yeah. And ChatGPT strongly suggested that I should not use this deep elasticity, but I forgot to return it back, so sorry. This is for the 2D elasticity. What I meant originally by this is that if you increase the dimension, go to 3D, you will get exactly the same set of equations, only these objects are again a bit more equal. In principle, it works in the same way. The bonus is that you do not need to distinguish between plane stress and constraint because you are in a 3D situation. The equations look almost the same, but now I have 3 displacement components, 6 independent strain and stress components. This matrix is 6 by 6, and you can see the phase how it looks like. So although the equation looks the same, the manipulation that is quite more involved, and even the ways it can lead quite easily to problems which are difficult to solve on conventional computers. So these are the governing equations of elasticity we would like to solve. Unfortunately, you already know either from the theory of elasticity, or even from the arguments which I was presenting before, that this is not enough to solve my problem. In order to get one solution for my problem, to have any uncertainty in there or arbitrariness, if you wish, you need to supply some extra facts about that. Information on how your structure interacts with the environment, and there are 2 types of boundary conditions in elasticity and related theories. So first ones are kinematic, so these are the ones which are presented here, and these are static. I'll count what these symbols mean. This gamma U and gamma P. This is just some part of the boundary, which I will just introduce in the next slide. So this gamma means that I'm not writing them in the interior of my structure, but on its surface. And there are of 2 types. The kinematic conditions tell me that these 3 independent displacement components are no longer unknown, they are known. So this is something which is easy to digest. The thing which is a bit more difficult to digest is what is written on the right-hand side. If I deliver blank short, then actually for each entry here, I should have written down that it depends on X, Y, and Z. But if I do that, then the formula is too long to squeeze it into one slide. So I decided to be less obsessed with this explicit dependence. And again, this is something copied from the elasticity materials, basically. This is in Cauchy, but Cauchy pyramid, so this is called sometimes used. And it is related to the fact that you can write down the equation at a boundary. So this is the part of the boundary I'm talking about. Which I got basically by taking some point of interest like this one. Again, just separating it from the rest of the structure by this elementary short pyramid. But now I find out that because there is surface, I'm missing a bit of my structure, and on that surface I have some forces acting. What is a bit inconvenient is, however, that these are of different nature, so these are external forces. But these are forces which are defined over the surface, hence there are a associated with some surfacing intensity. So these are forces which are defined per meter square, and they are also different from stresses, which has this different component. This is just conventional vector in 3D. So the terminology I will be using from this moment onward is that these are so-called external tractions, because these are not stresses per se. They can be equal to some stress components, for instance, but they are not exactly the same, because just in terms of plain numbers, there are 3 components of fractions in 3-dimensional elasticity, but 6 components of stresses. Okay? And here I would again like to remind you about this nomenclature I have been using previously. What I did not manage is that there also should be on this bottom bottom plane. But I just also distributed information there, and it was very hard to fit it. So I will just now, cheat a bit and enlarge it. So basically what I'm showing here is that, for instance, on this part of the internal part of the body, I have this normal stress component and 2 strains. With respect to the coordinate system, this normal component goes in the opposite direction. So the other ones, they have no other chance than to follow. So this is how the positive normal and shear forces can be oriented. On this bottom area here, so on this bottom section, I have this normal component, which if pointing out of this pyramid, it will move downwards, point downwards opposite to the y-axis. So now these shear components, if positive, would be oriented in this direction. And the part which I didn't manage to squeeze in the picture is that I have also the third area or plane, if you wish, hidden here. If I just look what is the normal component, it is actually proportional to the z-axis, so this is the sigma z. And because this points opposite to the z direction, I also need to orient the remaining ones accordingly. So this will go down and this will go left. Now, so this is then tau z, z x, but I know that I can interchange the order, and this is tau zy. So again, this is something which Jan or the teachers from Stanford Materials explained. And what you do again in this general exposition to elasticity is that you now write again 3 equilibrium equations. The equations, what is happening in the interior of the structure, and the exterior. And after some geometrical consideration, it actually turns out that everything has very similar structure to the situations of equilibrium, but instead of doing this partial derivatives, you have some factors here, x and y and z, but these are nothing else than the components of this outer normal vector. So again, this is the vector which is perpendicular to the plane. Now this inclined one is dimensionless and has the magnitude of 1. Dimensionless. In terms of physical units, again, this is stress. So this is in pascals. This is also in, this is the component of this normal vector, so this is dimensionless, because I forgot to write it here. No, sorry, and this is in Newton per square meter. So some people call it stresses because they have to unit of stress, but this is different. This is really not stress component, this is traction. Only if you are so obsessive about terminology or distinguishing two things from each other. So this is pretty much it. So you will have, you position yourself in a part of the boundary, you correct this autonomous vector, you determine its components, and then this must hold to satisfy the equilibrium on your surface. So for instance, if these are zeros, then it says that the stresses and their components in this part of the boundary cannot be arbitrary. They must somehow combine together to produce zero. So now how this all aligns in the two-dimensional elasticity, which by the way is exactly how this is usually used because nobody is interested in all these complicated three-dimensional pictures. So I would again like to remind you that I have this omega, which is my body. And the question, I will have gamma, which I will denote as boundary, because I'm talking about boundary conditions. So this is the same object here. And I will distinguish two parts of the boundary in elasticity, at least in the standard way. You can make your life a bit more complicated, but here it is not really needed. So I will have a part of the boundary when my kinematics is fixed. So if this is a dam, this is the part of the structure which is connected to the foundations. So here I assume that I have some u and v given. Usually in the models is equal to 0, or if I have some prescribed settlement, because I actually deform the structure beneath, I will I usually take some values. So this is the part of the boundary gamma u I was talking about before. So this is the part of the boundary you do not need to solve for displacements. You have that even as a part of it. The remainder is the part of the boundary which is subjected to forces, to this tractions. So this is the part which I call gamma p. And again, it collects everything which is not kinematically constrained. Because if I'm, for instance, in this part of the boundary, in here, I have zero traction acting there, and as I tried to convince you before, the stress just in the adjacent points to the boundary cannot be arbitrary. It must be in the way that if converted to these tractions, you must get zero. So it says that the behavior is different. The vicinity of the surface that in the okay. So some people like to say that this gamma is gamma u plus gamma p, or we can call it differently, but what I want to say is that if we combine the points in which I know the displacement vector and in which I know the fractions, I will see over a given quantity, I obtain all information around. And then there is this observation that you know one or two, you know the other one. But all of you actually nicely demonstrated this knowledge in the midterm test. So this is when you say you either know this distance or you and you do a little reaction or vice versa. So here this is exactly the same. So then, as a consequence, actually, if you have a loaded part of the boundary, like here, you will see that you have the same story as above, with the exception that there are no Z components, because of the reasons I was trying to explain very carefully in the previous part of the lecture. So if I then do the standard cancellation, actually this is what remains, there is nothing, nothing is happening in the Z direction, this is gone, and everything depends on two variables. So if I now do it in the way as indicated, I will denote this 3 by 1 column again as sigma at x, which is in the interior. Logically, this is just evaluated at the same point. In terms of the equilibrium equations I'm trying to reproduce in here, I have this sigma x and x plus 2xy and y equals to px over bar. So I should have prepared this part here. Yeah, and here I'm just modifying it in the way that here I have the shear and normal components, and they, when weighted with the normal vector coordinate, components, they must combine. So in order to write this down, I will, for the final time, hopefully, below this argument, to see that this sigma x gets multiplied by an x. There is no dependence on sigma y, so there's nothing, and this tau xy gets multiplied by y component. There is no sigma x in the second equation. This nx actually appears here, and here I have ny. So again, if you just do this comparison of how this partial derivative look like, this goes exactly the same logic. Hence, with a bit of inconsistency, I will actually write here that this is some n transpose, where this n in here is technically speaking different from this one. But I do not know the filling latter. So these are just normal components we ordered in a way that we can write down the stuff. And I'll come to that in the concluding argument of this. So what is missing also here is that I need to complement those. This is just straightforward cancellation of zero terms. So what I'm saying is that I'm searching for these two components of u and v. They depend on x and y, and they are just given as a part of solution to my problem. So this is how the kinematic boundary condition. And now I could have, tried to convince you this is exactly the structure of boundary conditions of one elasticity, displacement, or even stress. Of course, but if the cross-section is zero, so that's pretty much the picture. It took me a bit longer than I planned as usual, but the remainder of the story is not overly complicated, I would say. And in the remaining 13 minutes, I would like to finally give you yet another look on some object which is actually quite important if you like to interpret the results of two-dimensional elasticity. And these are so-called principal stresses. So does this ring any bell? Have you heard about the principal stresses before or not? So the thing is that this x, y, which is written here, means these two particular coordinate axes. Right? If I just decide to select a different coordinate system, usually people plot here some rotated version, so some x prime and y prime, then actually these components will change. So because I'm changing my coordinate system, then the normal and shear components would change. So if I would analyze my structure based on these values and deduce whether the structure will fail or not, I might encounter a situation if I choose my coordinate system differently, then the structure would fail. If I choose it yet differently, it will be okay. So what I mean is that this sigma x, tau xy, and sigma x are tied to coordinate system. So they are inherited from the choice of coordinate system. And I did really serious effort to explain in the rest that this is indeed the case, which means that they are, in a sense, depending on this particular choice, which in the jargon of mechanics is called, these are not objective. They are not independent on the choice of coordinate system. So again, if I would like to formulate randomly some failure criteria for my material based on these quantities, this is fundamentally wrong, right? Because again, for different choice of coordinate system, I will get different stress values. Sigma x, sigma y towards y, and I will reach different conclusions. So now the story can continue in two different ways. One is something which you for sure they have heard before, meaning that you take your coordinate system and start rotating it. You will have a look at what these new normal stresses are, and you are looking for the maximum stress value. You will see, and once you find it, you freeze it in this particular case, and you will find the most dangerous orientation, the weakest plane in which the structure can take focus. There is also a different interpretation which I would like to present now, which is related to the fact that actually I have this transformation relation ready, and what I'm interested in, if I'm given my sigma x, sigma y, and tau xy. So I'm interested whether there is this normal vector, so this one, which actually indicates the orientation of some section within my material, such that this P, and here I will delete this overbar now because now this is not a given. This is not a given outer traction. These are just tractions again constructed in the interior of my elementary volume. So now I'm getting inside the structure. Such that the traction is equal to some constant multiplying the normal vector. So what I'm in particular interested in is that I'm trying to rotate this plane, or segment if you wish, in a way that if I do this transformation, I will find out that actually this P points in the direction of the normal vector, which if you think it over, is actually the most dangerous orientation of that segment. Because if you have material sensitive to to tangent, which is typically concrete, then actually on this particular orientation, it will break because it will experience the maximum load, and this is what is orientation of the press. Okay? So on the other hand, if you see some structure which is fractured by some series of parallel cracks, well, educated guess is that it experienced the loading which is perpendicular to these cracks. If you have material sensitive to tension, which in structural engineering is often the case. Okay? So I'm interested in this question. So if I'm able to find this orientation of the most dangerous direction, usually a structure can fail if it doesn't like stresses, which are tensile. So now for that, and this is a bit inconvenient, we will rely on yet another representation of stresses. So I have the one which is just on the previous slide, but if I would like to highlight that actually these stresses are something which is called second order tensor, it is actually more natural to orient those or represent those as 2 by 2 matrix, which means that actually now this transformation out of sudden makes more sense, because this, reshuffling of the normal coordinates, of the components of the normal vector, this was just before, because I decided at the very beginning of the lecture just to start the stresses in this particular way. So this is the formulation which preserves the fact that this is normal vector, this is normal vector, and actually this needs to be this matrix second order tensor. So this is something which is more physical or geometric version of writing down these equations, and this is exactly how Cauchy did that, by the way. This is something which is more convenient for computations and was developed in late 50s, 60s of the last century, so there is hundreds. So just to make the distinction, I will write down that this is something called A of sigma, where A is just arbitrary number. This is my n, my outer normal vector, and this is my p. So basically what the problem which I'm solving is that I'm taking this stress components arranged in this 2 by 2 matrix in this particular case, which gets multiplied by n, and I'm curious whether I can find n such that I can get the outcome of that operation proportional to the normal. So there are no shear components, tangential components. And I would like to highlight that the original question was, is there any n? So this is my n. So now what I can do is to write down the following equivalent form of that. So what I did is that I took this thing, I translated it to the right hand side, and to have this in the way which is more convenient, I just multiply it by this units or identity matrix, not to change anything. So basically what is the system of equations I'm solving is that I take this original stress and I subtract from it the multiple of identity. And I'm interested that I can get some solution of this equation different than 0. Because if this n is equal to 0, of course this is satisfied, but it gives me no information, and the norm of 0 vector is not 1 certainly, so this is not a valid solution for me. So I'm actually trying to find out if there is an n for which I can solve this equation with 0 on the right hand side and still not force this quantity to be equal to 0. And if you just think it over, and I'm already approaching fast the end of the lecture, or am I over time?
It's already over time.
Oh, sorry. So then this, please next time be a bit more explicit, because if you start reading, I just think that you are bored with my poor explanation of that my time is over. And there's no way to distinguish that. So I'll follow up next week, then I will eventually show how this is to be used in some numerical language.
Just for reference, we ended 6:20.
6:20.
Yeah.
But I don't.
It's even recorded. Oh my gosh. Sorry, I thought that. Yeah. So I'll try to finish 20 minutes earlier. Wow. Sorry. My bad. Yeah. Yes, I'm listening. I just need to. Yeah, thanks again for this nice promotion. You do not have our very specific Czech accent. So
I have a question. So I want to say the reference is file, but I can't seem to access it.
okay, so then please try to write me an email. I uploaded it in a weird way. And if I uploaded your solution with no corrections or no red marks, uploaded the old version of the file.
What did you say about the solution with no red marks?
Yeah, so what I should have done ideally is that I took everything what you sent to me, for each of you converted this to PDF, then graded all PDFs and uploaded them back to Moodle. But it might happen that actually I uploaded a version which has not been graded yet. So if this happens, then let me know. I have it stored here and I will just upload it. But what I was trying to say at the beginning of the lecture is that overall the results were quite okay, I would say. Yeah. And if you do not like them, then you can always resit the test if you wish. Yeah, or we can do it before the end of the year. But actually, I should announce this next week, starting with, at the beginning of December, because usually I forget and this is last minute event. Yes, you wanted to discuss something. So, sorry, I still didn't send your request to make the department of the
No, I'm trying to get some access to my school
Okay.
and reach out to them. But yeah, your help would be great.
That's a bit. I also saw that the results are 100%. So to say, so if you need some discussions or some additional explanation, let me know, but please in advance. My schedule now is a bit tight, so.
So, for example, which day of the
Yeah, so we just have it. Yeah.
because my timetable is much more flexible.
So what I recommend, but I cannot, of course, force you by any means,